All right, so we're going to move on to learning targets 4 and 5 of Unit 4, which is going to deal with the structure of an atom. So what is an atom? So what is the difference between protons, neutrons, and electrons, which are these subatomic particles that make up an atom? Big thing, two big things really, well, three. Number one, where they're located. Number two, their size. And number three, their charge. So protons are located within the nucleus. They have a relatively large mass as far as subatomic particles are concerned, and they have a positive charge. Neutrons are also located in the nucleus. They have about the same mass as a proton, but they do not have a charge. And then electrons are found orbiting the nucleus in electron clouds. They have a lot smaller or a much smaller mass than that of protons and neutrons, and they have a negative charge. So this is a visual concept of what an atom looks like. This is an example of a Bohr model. Remember that electrons are not found in nice, neat little orbitals. They're in clouds, energy levels, and they can change up and down based off the amount of energy available. So each element has a unique number of protons. This is going to be known as their atomic number. It's kind of like the element's identity. Unreactive atoms have no overall charge. That is because they have an equal number of protons and electrons. So that means the number of positives and negative are the same, and that means that the charges will cancel out. The electric force that holds together, the electric force holds the atom together. Positive protons are attracted to the negative electrons by this electric force. This force holds the atom together. So let's say, for example, we're analyzing a aluminum atom's properties. As we conduct experiments, we discovered that aluminum atom has 13 protons and 10 electrons. What do you think the overall charge of this atom is? Well, you have 13 positively charged ions, and you have 10 negatively charged ions. So 13 positives minus 10 is going to be 3. So this particular aluminum atom has a overall charge of plus 3. What do atoms of an element have in common with other atoms of the same element? Atoms of each element have the same number of protons, but they can differ in number of neutrons. And this is going to give way to isotopes. Okay? Remember that the atomic number is the number of protons, and that's kind of the fingerprint of each atom, or each element, rather. Every element of that element is going to have the same number of protons. That's what makes it what it is. But we can change the number of neutrons within it to add more mass or take away mass. All right, so most periodic tables, the top number is the atomic number, tells you the number of protons. Then you have the chemical symbol, then the name, and last down here at the bottom, you have the mass number, and this is typically the addition of the mass or the weight of both protons and neutrons, because that is where majority of an atom's mass is found. The atomic number equals the number of protons, and the mass number equals the total number of subatomic particles in the nucleus. And there you have the definition of both. Okay, remember, atomic number, number of protons, mass number, the sum of the number of protons and neutrons. So in class, we'll do this. You can pause it and practice this if you want to. So label the numbers of the element on the periodic table. So 11 is going to be the atomic number. 22.990 is going to be the atomic mass, or the mass number. Right, so as you can see, nucleus, the atomic number equals the number of protons. So let's say the red particles are our protons. We have 1, 2, 3, 4, 5. So it has an atomic number of 5. But the mass number is going to be the addition of both. So you had 5 red ones, 1, 2, 3, 4, 5 white ones. So you'll have a mass number of 10. So the question is, with isotopes, why do isotopes have the same element have different atomic masses? Well, isotopes of an element vary in mass because their numbers of neutrons differ. So here are 3 different isotopes of hydrogen. We know it's hydrogen because each of them have one proton, and that's unique to hydrogen. But what we see is different numbers of the white particles, which are our neutrons. Okay, so here we have one neutron, here we have no neutrons, here we have two neutrons. These are all hydrogen because they each have one proton, but they're going to have different atomic mass because of the addition of neutrons. Some isotopes are more common than others. Radioisotopes are unstable isotopes that emit radiation and decay into other isotopes. The number of neutrons can be calculated. So the number of neutrons equals the mass number minus the atomic number. Okay, so mass numbers up here, atomic numbers down here in this particular example. 35 minus 17 gives us 18 neutrons in this particular chlorine molecule. 37 is a mass number, and then 17 again is the atomic number for chlorine. 37 minus 17 is 20 neutrons. Both chlorine, because they both have the atomic number of 17, which means they have 17 protons, but they're isotopes of each other because they have different number of neutrons. All right, so let's say that we have a sample of magnesium or Mg. The sample of Mg has a mass number of 26 and an atomic number of 12. So based off the last slide, figure out how many electrons, protons, and neutrons this isotope has. Well, it has an atomic number of 12, so that's going to tell us how many protons it has. And we know that atoms on a periodic table that are unreactive unreacted have the same number of electrons as they do protons. It gives them overall charge of 0, so they have 12 electrons. How we find the number of neutrons is you do 26 minus 12. You take the mass, which is the sum of protons and neutrons, subtract 12. Okay, so that's going to give you 14. What unit is used to express atomic mass? Because working with such tiny masses is difficult, atomic masses are usually expressed in unified atomic mass units. Unified atomic mass units is a unit of measurement or unit of mass that describes a mass of an atom or a molecule. Average atomic mass is a weighted average. Isotope abundance determines the average atomic mass. For example, chlorine 35 is more abundant than chlorine 37. So chlorine's average atomic mass is closer to 35 than it is to 37. The mole is useful for counting small particles. Mole is the SI base unit used to measure the amount of a substance whose numbers of particles is the same as the number of atoms of carbon in exactly 12 grams of carbon-12. 1 mole is that really long number of particles. So the number is usually written as 6.02 times 10 to the 23rd, and this is called Avogadro's number. And here is a nice little visual concept or component to remind you of what a mole is. You've got moles talking about Avogadro's number. So moles and grams are related. Molar mass equals the mass in grams of 1 mole of a substance. For example, 1 mole of carbon-12 atoms has a mass of 12 grams. So the molar mass of carbon-12 is 12 grams per mole. You can convert between moles and grams. And here's the conversion rate to go either way. If you start with moles, then you have the molar mass of the element divided by 1 mole. Or if you start with mass, you have 1 mole of the element over the molar mass. All right, so to find the molar mass of a compound, add up the molar masses of all of the atoms in a molecule of the compound. Example, finding the molar mass of water. Molar mass of oxygen is 16 grams per mole. The molar mass of hydrogen is 1.01 grams per mole. Molar mass of water is 2 times 1.01 grams per mole plus 16, which is going to give you 18.02 grams per mole. And that is where we're going to end. Be sure you complete the video form. We'll do more practice with this soon. If you have questions, please let me know.